In this video, I want to make a summary of some of the nucleophiles, carbon nucleophiles and then hydrogen nucleophiles, like kind of summarizing what is the type of reaction that we expect for those reagents. So, starting with hydrogen nucleophiles, we're going to say principally they are hydrides. So, H nucleophiles. And these reactions are reduction reactions. And here we will be using lithium aluminum hydride and sodium boron hydride. Essentially, what these reagents do is transfer a hydride. So I'm going to write that down. If you have same mechanism for aldehydes and ketones, so I'm just going to draw here an aldehyde. So if you had lithium aluminum hydride, the structure will have a central aluminum atom and 4 H's. So aluminum is formal negative charge. And here I have a counter ion, so lithium and aluminum hydride. What happens next is this will transfer a hydride. So that's the nucleophilic attack. And the reaction here is the mechanism is nucleophilic attack, and then we need a step proton transfer. When you're doing the product prediction, in this case, you want to form, first you're going to add an H, as you can see here. Therefore, when you open this up, you're going to have H and H, so an extra H, as we can see. Starting from the aldehyde, and then we're going to have, in another step, add water, for example, and we will form the alcohol. Now here, I have started with an aldehyde, and when you protonate it, you form a primary alcohol, aldehyde. If that was a ketone, you will end up with a secondary alcohol. So in that reaction, it's a reduction reaction. You're going to get the same if you do that with sodium boron hydride. The difference between these two reagents is that this is not as reactive. In other words, it reacts slower, but we can use, one advantage is that we can use sodium boron hydride with product solvents. So you may see when you're doing your reactions and predicting products, you may see that this is accompanied with a product solvent, such as methanol, ethanol, or water. The reason you can do that is that the reaction with the solvent is slower than the reaction with the aldehyde or the ketone. So you can do that. But lithium aluminum hydride is much more reactive, and it will react immediately with the product solvent. So you need to do this in 2 steps. If you're using this, you have 1 step in a dry product solvent, and in step 2, you add water or even acid. This can be 1 step. So advantage to that. But these are the 2 reactions are reduction reactions, and you're making alcohols from aldehydes and ketones. Now let's go to the carbon nucleophiles. So I'm going to erase that. And here with carbon nucleophiles, we have several. So let's see what we have. Starting with Grignard. So now I'm going to have, let's erase that. So carbon nucleophiles. Reactions that we will have are the following. So Grignard, and a Grignard reagent is in this general form. So that can be, for example, metal, magnesium bromide, phenyl magnesium bromide, and so on. Depends on what you want to synthesize. So Grignard is one type of carbon nucleophile. Another reaction with carbon nucleophile is to make it react with cyanide and form the cyanohydrine product. And another reaction is Wittig. And all of these reactions add carbons to the skeleton of the molecule. So if we want to make it bigger, larger, these are the strategies that we need to do. And so Grignard is a strong base, a strong nucleophile. We cannot have water with this. So we need to use that in dry conditions. So if you have the reaction, and let's say that I'm doing acetone, and I want to add one more carbon, say that I want to do metal magnesium bromide. In that case, we can write this reaction as positive here, negative here, and you will have a nucleophilic attack over to the ketone. And I'm going to draw the product. Let's do this. So now I'm going to have O negative and one more metal group, the one that comes from here. And that's a step one. Here you need to use dry ether, for example, diethyl ether. And in a second step, you add water or maybe some acid. What you do is the protonation of the alkoxide to get the final alcohol. So that is the butanol, right? And you started from a ketone because you added an R group, an alkyl group. So ketone, you end up with a tertiary alcohol. If you started with an aldehyde, and that's, say that we do the same. So metal magnesium bromide. Step one, this is dry diethyl ether. We will add one metal here. Remember, well, let's draw it. There is an H here. Okay, H, I'm adding a metal. That's plus, negative. Remember that, nucleophilic attack. Same, and we are forming the alkoxide. And now I'm adding a metal, that is my nucleophile. And in the second step, I will do the protonation of the alkoxide. Now the alkoxide here, as you see, is a secondary alcohol. But again, the idea, we're adding carbons to the chain. We'll have one more carbon. So here from the ketone, you get a tertiary alcohol, and from the aldehyde, you get a secondary alcohol. So that's one of the reactions to add carbons to the chain. If we do that, that is Grignard. So this is this reaction, right? So the other reaction with the cyanohydrine formation is make the carbonyl compound react. The nucleophile here is going to be cyanide. And typically you have, say that you have acetone, and you have, we often use this condition, Kc and HCl. That's going to form cyanic acid. So here, the nucleophile is the cyanic group, and you will be making here, this is O negative, and you will have Cn here. That is now, that once you have an organic compound that contains that functional group, it is a nitrile. A nitriles are very useful. Once you have here, let's do the protonation. You will have OH. This is your cyanohydrine. That can be hydrolyzed, and the nitrile becomes a carboxylic acid, OH. And nitrates can also be reduced. Say that we use lithium aluminum hydride. And in that case, we will have here's one more carbon and then the amino group. So versatile, we can go several directions. Point is that we had added one more carbon here from the cyanide to the chain. The last reaction that adds carbon to the skeleton is the Wittig. And Wittig is a little different in the sense that you will transform a carbonyl into an alkene. So you have this, and you make it react with, first, say that we're making that in steps. we're doing triphenyl phosphine and make that react with methyl bromide. In that step, you will be making an SN2 reaction. When we do this, phosphine, you have a nucleophilic attack here. That's an SN2 reaction to form the following. So that's the three. Here you have now a phosphorus with formal positive charge. And the Wittig reagent is made, so step 1 and step 2, you use, for example, butyllithium as a base here. This is negatively charged, so the conjugate base of butane and lithium counter ion. That's a very strong base. And that will remove one of the H's here to form the ylide. The ylide is this species with these two charges. So after removing one H, ylide, and we have a resonance structure that we can make. And the resonance structure is the following. And what we have here is what we need to be paying attention to. This is where you're going to insert in place of the oxygen. So when you're doing problem with carbonyls, you need to remember that this will go here. So the final product after the Wittig is an alkene. In this case, that will be a sister. Or simply, remember, we in line structures don't draw the hydrogens attached to carbon. So that is the summary of the reactions that we have seen with carbon in hydrogen nucleophiles.